Well, thank you very much. I'm very grateful to Al and Johannes for the invitation, and I'm very pleased to talk to you about this. I've heard the joke. I don't know if it's a joke or just a fact that there's a certain age after which if one hasn't learned algebraic geometry really, that one never learns it. If that's the case, the age that I've heard quoted is 40, and I'm well beyond that. And I will not be giving an algebraic geometry talk. I don't know that I'm qualified to do that, but this is a topic that has tied in a lot to algebraic geometry, and I'm using in my study of cluster algebras a tool that that originated in algebraic geometry. So what I'd like to do today is talk about scattering diagrams. Just a quick overview of this sort of, and if you know about scattering diagrams, because they do come up in algebraic geometry, I know, this might sort of seem like a very narrow or different point of view, and it's because I'm talking about scattering diagrams as they are most useful for cluster algebras. I'll then give a brief overview of cluster algebras. Again, each of those could be the topic of courses, so I'll be giving a very brief overview indeed. And I'll talk a little bit, I guess the scatter in the second scatter in the title is referring to scattering amplitudes. As far as I know, it's just somewhat accidental that those two words both those two terms both contain the word scatter. And I'll be just very briefly just mention why somehow this ties into some physics. And then I'll spend a bit of time on combinatorial models. The mutation section at the end, I think I almost certainly won't have time to talk about. It's a little bit of the talk where I would be able to talk about some of the methods one might use to prove things, and I just to give a very brief account of that right now, since I probably won't get to say much about it. The idea is that you have in these scattering diagrams some sort of symmetry, and you're exploiting the symmetry. The symmetry just has to do with matrix mutation. So I'm expecting that's probably all I'll be able to say about that last section. But let me get on now with an overview of the talk. So scattering diagrams arose from mirror symmetry. Cluster algebras arose in the study of total positivity, and then starting really 20 years ago or so, there started to be all these connections found to algebraic and geometric areas. And physics and some surprising ways that things were connected. And in fact, it turned out that some of the work that had already been done before even the definition of cluster algebras was actually doing some things that we would call cluster algebras now. So cluster scattering diagrams were applied by Gross, Hackenkiel, and Kontsevich to prove some long-standing conjectures about cluster algebras. And then more recently, there was this connection discovered between cluster algebras and scattering amplitudes in physics. And let me just say, one of the things that we'll care about is something called theta functions. So when you have a scattering diagram, you can talk about theta functions. You can think of this scattering diagram somehow as the device, and the output is a bunch of functions called theta functions. So my goals today, I want to introduce and connect scattering diagrams and cluster algebras, connect them to each other. Very briefly mention the connection to scattering amplitudes in physics, and then just survey the state of complete combinatorial models for cluster algebras and cluster scattering diagrams. And that word complete, there are a lot of models that might give part of the picture also, and those I actually know a little less about, but this talk is going to be focusing on models where we have a hope of actually modeling the entire picture in one combinatorial model. So let me get on. So scattering diagrams first. So the basic setup is that you have a skew-symmetric matrix, a vector space and its dual, and you have integer points that we're going to in both spaces, and those will correspond to Laurent monomials. So more detailed, our skew-symmetric matrix will be called B. It'll have integer entries. Some people in the cluster algebras world are thinking about things with non-integer entries, exchange matrices with non-integer entries, but we'll be doing integer entries, and this skew-symmetric matrix we'll call the exchange matrix. So our real vector space is going to be V. We'll call its basis alpha 1 through alpha n, and if that makes you think of simple roots in a root system, yes. It has a dual space. That basis will have dual space will have a basis, that's row 1 through row n, dual to the alpha basis, And we'll just use this fairly standard way of writing a monomial by saying x to a vector, and we mean that the vector is, we're taking coordinates in that basis to get a monomial. So a scattering diagram. A scattering diagram is nothing more than a set of walls. So, and a wall is something geometric plus something algebraic. So each wall is a codimension 1 cone. We'll put it in the dual space, and it's decorated with a scattering term. And a scattering term is a formal power series in the y hats. Y hat. So the y hats were the things that came up in these monomials for indexed by things in the space itself. So we have this cone, and we have a formal power series decorating it called a scattering term. Slightly more detail. Each wall has a normal vector. So the wall lives in the dual space. It has a normal vector in the space V, and we'll take a primitive. Each wall has to actually be normal to an integer vector, but we'll take a primitive positive integer vector. So the wall actually has to be normal to a vector with non-negative coefficients. We'll take a primitive one, meaning that there's not a smaller integer vector that's a scaling of it. The scattering term is not just a formal power series in all the y variables, but it's actually basically a one variable power series, because we take y hat to the beta as our single variable in the power series. So we have powers of y hat to the beta, where beta was this primitive normal vector to the wall. And there's a certain finite condition. The finiteness condition, we allow infinitely many walls, but there's a finiteness condition that says basically that everything we want to do, even though there's infinitely many walls, we can do everything we want by taking a limit of formal power series. And, just looking at, restricting to a certain degree of polynomial that we allow, and then letting that degree go to infinity. Okay, so wall crossing. A little bit of this, I suggest maybe letting your eyes unfocus if you can see where my mouse is moving, letting your eyes unfocus and not worrying perhaps about the details. But when we cross a wall, we're going to imagine sort of walking through this scattering diagram. When we cross a wall, something happens to monomials. So we have some monomial that we're keeping track of. We cross a wall, and a monomial in the x's gets replaced by itself times some power of the scattering term. So there's a formal power series sitting on that wall. We multiply the monomial times some power, and that some power of that formal power series. And if you like, the power that we take is just the pairing, since lambda is in the dual space and the normal vectors in the space, the pairing of lambda with the normal vector. And there's a rule for taking plus or minus, which depends on which direction we pass across the wall. A path-ordered product is something that we get by composing these wall crossings along a path. And this is actually where we need the finiteness condition, because our path might cross infinitely many walls, and so you can't make an infinite composition of automorphisms on some infinite composition of these functions that modify our polynomials or monomials. But what we can do is the finite condition basically says that up to any given degree, there are only finitely many walls, up to any given degree of y hat to the beta. Anyway, so it works out that you can actually do this even though you might cross infinitely many walls. We'll do an example right now where we are crossing finitely many walls. This here on the left could be my scattering diagram. You can see some walls with some scattering terms written, fairly simple example. If I want to apply the path-ordered product given by gamma 1, shown in the picture, I want to apply it to the monomial x1 to the minus 1. Well, in that first instance, I cross a wall and nothing happens. This minus 1 is really a vector. X1 to the minus 1 is x to a vector minus 1, 0. The normal vector is 0, 1. And so nothing happens because this power is 0. In the next step, however, we cross this wall and something happens. And it turns out that we replace x1 to the minus 1 by itself times the wall crossing term to the first. So we're crossing that wall, and we're taking that wall crossing term to the first power. On the other hand, if we take a different path connecting the same endpoints and apply that path-ordered product to x1 to the minus 1, we can in our first step, we actually cross this wall. We do exactly the same thing that happened in the second step for our first path. We cross this wall and pick up a change. In the second step, nothing happens to the x1 inverse, but we have this y1 hat, and it gets modified as we go. So the y1 hat is replaced by itself times the power of the wall we're crossing in the second step, and we get that. So that's just an idea of sort of the flavor of how this works together. Okay, I need to tell you the two most important concepts about scattering diagrams, because the scattering diagram example I just put up where there were just random rays going out was sort of a dumb example. Two scattering diagrams, first of all, are equivalent if they give the same path ordered products. So for example, this scattering diagram, does it have two walls or four? Right? I just said codimension 1 cones. My cones could be lines. My cones could be rays. And the answer is we don't care. They're equivalent. Okay? The next important idea is consistency. A scattering diagram is consistent if path-ordered products depend only on the endpoints of the path. Well, in our example that we saw, we had a scattering diagram that is not consistent. We calculated the path-ordered product applied to a certain monomial along one path, and along the other path we got different answers. It turns out, though, we can make it consistent by adding one wall. If we add this wall, right, it has a normal vector 1, 1. And so the very simplest non-trivial formal power series I can put on here is 1 plus y hat to the 1, 1, y1, y2. And if we now do this operation, we think about what gamma 1 does to x1 inverse. First step still does nothing, but the second step does do something. We end up adding 1 power. Again, I'm not expecting you to follow quickly enough to see why we added, this scattering term to the 1, but we added a power. We didn't add. We multiplied by a power of the scattering term, replaced x1 inverse by itself times the power of the scattering term, that scattering term for the wall that we crossed. And then in the next step, we cross this wall, and something happens to the x1 inverse, and also something happens to the y1, y2 hat. And that's our path-ordered product applied to x1 inverse now. And just to remind what the other path did, the other path hasn't changed. It doesn't see this new wall. And so we do this. If you do a very simple manipulation with this this gamma 1 path-ordered product, then you see you'll get the same answer as for gamma 2 now. And of course, to show that it was consistent, we would actually have to check it on all monomials, and we've only checked on one, but that's enough for this example. So consistent means if I'm going to do a path-ordered product, it doesn't matter which path I take, it just matters where I start and where I end. Cluster scattering diagrams. So this word cluster is going to refer to cluster algebras, but we'll get to that later. So the theorem of Gross-Hacking, Keelan-Kontsevich is that if you just start with a skew-symmetric integer matrix, an exchange matrix, then up to equivalence, there's a unique consistent scattering diagram that you make in this one particular way. So first of all, and I think I changed my notation at the last minute in this slide. Originally, this said D instead of scat of B, scattering diagram of B. So this should say scattering diagram of B contains the walls. And what are these walls? These are the basis vectors for my space. So these are coordinate. They're orthogonal. The hyperplanes orthogonal to them are just the coordinate hyperplanes. So I take the coordinate hyperplanes with the very simplest non-trivial power series that I could put on them. And then the rule is that all other walls are outgoing. And outgoing just means, well, there's a way that I can take my exchange matrix and my normal vector and make a vector in the dual space. So I do this matrix, do this multiplication, right? Or write beta in the alpha basis, do a matrix multiplication, and interpret the answer as a vector in the row basis in the dual space. And so we have to ask whether or not that the wall that we're putting in actually contains that vector. As an example, this wall that we put in is outgoing, and in this case, just to see how it hangs, the vector that we would have to avoid is actually here. If you can see where my mouse is waving, the vector that we would have to avoid is there, but that's fine. We put the other ray in that does not contain this vector in the bottom right quadrant. So this is the cluster scattering diagram in this example for this exchange matrix. And there's this T for transpose. I at some point decided how to write a T for transpose in there because there's two conventions you can use about basically whether you care about your rows of your matrix, or you care about your columns of your matrix. And I made the opposite choice from Gross, Hakenkiel, and Gitsevich for reasons that had to do with cluster algebras. So that's all that is. Okay, so vaguely stated theorem. If you have a consistent scattering diagram, then it cuts space into a complete fan, but not necessarily a finite fan. So, you can make the definition of a fan, just like, and we usually want to say that's a finite collection of cones that intersect nicely. But you can define, you can take away that requirement of finiteness, and that's the kind of fan that we get. And the reason this is a vaguely stated theorem is because what does cut space mean? Well, that was actually probably the hardest part of when I tried to prove this theorem, was I kept realizing that my definition of cut space wasn't quite the right thing. And then once you get to the end and prove it, you realize, of course, that was the only thing you should have ever written down. But anyway, the cluster scattering fan is the complete fan cut out by the cluster scattering diagram. Again, cluster scattering diagram, given a particular skew-symmetric integer matrix, there's one particular scattering diagram you write down, and it's consistent, and so it cuts space into the cluster scattering fan. All right, theta functions. I'm going to just try to do theta functions by example to sort of say what they are and what's involved in computing them. So theta functions, once I have a scattering diagram, so I fixed a scattering diagram, and for me it will always be the cluster scattering diagram. So here's our exchange matrix, and I think I am sort of generalizing a little bit. I said skew symmetric, but if you're familiar with skew symmetrizable matrices in the sense of Cartan matrices in Lie theory, so there's a skew. So there are symmetrizable Cartan matrices in Lie theory. So this is a skew symmetrizable exchange matrix in the same kind of sense of symmetrizable. So we'll take this just to give a slightly more interesting example. Once I have this cluster scattering diagram, there is for every integer vector, every rational vector, I should say, there's a theta function. Actually, I think I really do mean integer vector. So it's a typo. For every integer vector, there's a theta function. And what you do is you compute certain things called broken lines in this cluster scattering diagram, and you sum over some monomials you obtain from them. So let me try and give an idea, just a sense of what that is. So first of all, I'm going to take the vector -2, 3. So -2 row 1 plus 3 row 2, and theta sub that vector. The theta function that I can compute now, or show you now, will be that theta function. But for any integer vector, I can find a different theta function. So what I need to do is I need to first pick a point in my positive cone, in my positive quadrant. It doesn't matter where I pick it as long as it's sort of generic enough. So I pick that point. And what I'm going to do is I'm going to think about broken lines. And these are all coming in from a certain direction. And the direction is given by this vector. Okay, so the initial, I can think of these as actually, as paths in space, and parametrized, motion in the space. And initially the derivative is 2 row 1 minus 3 row 2, so the negative of this. So it's coming from this direction. So I take a bunch of paths coming from the direction that I care about. And there's some rules about how they bend. They bend when they hit walls or not. Okay, actually, so what I'm going to do before I let them bend at all, actually, is I'm going to decorate the paths coming in with monomials, and the monomial is x1 to the -2, x2 to the 3, which is again my initial vector. So this monomial is also sort of telling me the derivative of the motion as I'm following this line. And you can see, you don't know why they're bending here, and I'm not going to fully tell you, but you can see that these broken lines can bend at some walls, and the ones that I've drawn, after they bend at the walls, they come to the point P that I had chosen. Okay, and when they come to that point P, they pick up new monomials. Okay, the monomials that they pick up, it's something like, let's focus on this one, for example. this wall is coming in. What I do is I take the monomial that I have. It gives me a vector. I think about the normal vector here. I'm taking the pairing of those two, a dot product, if you like, -2, 3, dotted with 1, 0, and I essentially take an absolute value. In effect, I'm thinking about which direction I'm going, and so I get a power of 2. I get 1 plus 1 plus y1 hat, that quantity squared. So I get a 1 plus 2y1 hat plus y1 hat squared, right? And then the rule for scattering is that I pick one of those terms. I'm allowed to pick a 1. Right? So let's think about all the lines that scatter on this wall first, or that break on this wall first is what I should say. I'm allowed to pick a 1. The 1 would mean that I just go through this wall. For example, this broken line going off here, I didn't draw the whole thing, but it's coming off from infinity. It passed through this wall without doing anything. Okay. I could also take the 2y1. Right. Remember, I've got 1 plus y1 hat squared, and the square came from pairing the vector given by this monomial with the normal vector. If I take the 2y1, then what I do is I change this old monomial into a new monomial based on picking that 2y1, and I bend a certain amount. If I pick the y1 squared, I bend more, and an example is here. So I could have bent. You change my monomial by taking both powers of the y1 hat and going here. And you see some y's that are slightly different from y hats. We have to make a slight change of variables here. And anyway, what I want to just give you the idea is that we're taking broken lines, we're taking straight lines, we're letting them break when we hit walls, and there's some rule for how the monomial changes and therefore how the direction changes every time we hit a wall. And what we do is we think of all the possible walls starting and all the possible ways of bending, what are the ones that would have ended at P, right? I could have come here and broken and gone lots of different directions on these walls, but could I have gotten to the endpoint P? And if I could, I keep that. So there's, in nice situations, there is a finite number of broken lines that actually could end at P, and we take their final monomials and we add them together. So the sum of all these monomials that are shown here is the theta function. That, just to give an idea of how this looks. So recap, scattering diagrams. A scattering diagram is a collection of walls. A wall is something that looks like a codimension 1 cone with a scattering term that's a formal power series. Path-ordered product, we're going to do some operation on monomials at each wall crossing, and we're going to take a composition along the path. Consistent scattering diagram means that path-ordered products depend only on endpoints. And the clustering scattering diagram, the cluster scattering diagram is this particular scattering diagram that we define that depends only on the exchange matrix that we started with. Theta functions, we have to do this thing where we have to find all possible broken lines. And for some reason I keep saying rational lambda, but I really mean integer lambda. There's a whole slew of theta functions that we get. So any questions at this point?
There's nothing.
Questions at any point are still fine. Let's talk about cluster algebras. This will be very much a cartoon version of cluster algebras, but we start with an initial seed. It consists of initial cluster variables, and we'll just call them x1 through xn. We also start with, again, a skew-symmetric integer matrix B, and if you press me, I'll let it be skew-symmetrizable. And we have this operation. So we have something called a seed. It's an initial seed. It has the cluster x1 through xn and the integer matrix B. And once you have that, you can mutate. So there are n directions for mutation, and the n directions are basically the n cluster variables, the n initial cluster variables that are in a seed. Mutation does two things. It takes out one cluster variable, and there's some formula using the exchange matrix and the other cluster variables to replace it with a new rational function. So then the new thing will be a rational function in the x1 through xn. And also there's a way to change B by matrix mutation. That's the part of the talk where we actually talk about what matrix mutation is in a lot of detail. Will come later. I'll just mention the definition quickly here, but the result's a new seed, and mutation's an involution. So if I do mutation in the same direction twice, it comes back. And so in effect, what I have is this sort of infinite branching tree. I have my initial seed where I have an exchange matrix B and my initial 3 cluster variables. If I mutate in direction 3, I have a new seed where I'm just using the notation mu3 of B for the mutation of 3 and the mutation of B in direction 3. And I've got a new cluster variable, which I'm just calling x3 prime. If I mutate back in direction 3, I go back home where I started. But if I now mutate in direction 1, I go to maybe some completely different seed, or if I mutate in direction 2, etc. The cluster algebra for the given initial seed is the subalgebra of the field of rational functions generated by all cluster variables. And that might seem like a crazy thing to do. You have this infinite branching recursion, and then you take all cluster variables and let them generate a subalgebra, or really a subring of the field of rational functions. But this actually, in a lot of cases, a lot of interesting cases, might give you something that's the the homogeneous coordinate ring of some variety that you care about. And so it's one of these things where the definition looks strange, and somehow by the connections to so many other areas of math and even physics must have been the right thing in some sense. Okay, so some slight details about mutation. Again, feel free to let your eyes unfocus on this. Matrix mutation, if you just change the entries and think about how each entry changes. If you're looking in row or column K, K is the direction where we're mutating. If you're looking in row or column K, you just negate the entry. And in the other rows, you keep the entry and you add some bit that depends on, well, what does it depend on? It depends on the entry that was in row I. I'm looking at entry ij here. It was in row I, but column K. And also the entry that's in row K, but column J. So you're sort of moving over to the, or up to the kth column row. Now, strictly speaking, I'm going to need something called principal coefficient. So really, I'm going to just tack on some extra to the bottom of my exchange matrix. But I'll only mutate in the directions 1 through n. And I'll just carry along this same formula for the lower part of my matrix. Also, there are some exchange relations. And I think it's pretty safe to let your eyes unfocus and just look at the form of this equation. But I'm taking xk is my old cluster variable, xk prime is my new cluster variable. And I'm going to, so basically this means xk prime will be this sum of 2 terms on the right divided by the old xk. And the terms are products of cluster variables and also some coefficient variables in the old cluster. And they're determined by the exchange matrix B. The y1 through yn are certain indeterminates that we just use as coefficients. Okay, so that's details without details in some sense. Just an example to show, again, what this kind of looks like. If I take my exchange matrix B and I just extend it by putting a little identity matrix below it, I'm going to get these cluster variables. These are my first 2. When I swap out x1, I'm supposed to get, well, it's some sum of 2 terms divided by x1. And that's it. So this is like, we could call this x1 prime. It would probably make more sense to call it x3 in some sense. If I then swap out x2, so now my current 2 cluster variables are x2 and this x1 prime, and I need to find some monomial, some sum of 2 terms that involved x2 and x1 prime, add them together and divide by x2. When I do that, I need to put it over a common denominator. So I'll get an x1 in the denominator also, and then we continue on. There's a nice change of variables, and this will be the key to tying it together with scattering diagrams. So what we can do, and this is following Fomin and Zelevinsky from one of the foundational cluster algebras papers. What we do is we can sort of look at the column of this extended matrix, and we can think, somehow this, the first 2 rows were x1, indexing x1 and x2 in some sense. The next rows are like y1 and y2. And I'm going to look at this column, and I'm going to get a monomial, and it's going to be y1, because I have a y1 to the 1, y2 to the 0, really, for that bottom 0, y1 to the 1, because I have a 1 there, and then x2 to the -1. So I get it, and I'm going to call that y1 hat. And these will become the y1 hats that we saw in scattering diagrams when we tie things together. Similarly, I can look up and down this column and get a monomial, which I'll call y2 hat, which is y2's times a monomial of the x's. If I make that change of variables, these cluster variables become somehow simpler. What I end up with always is a monomial in the x's times a polynomial in the y hats. And this is a result of Fomin and Zelevinsky from that paper, that early foundational paper. If you have a great memory for mathematical symbols, and I know that there's some subsets of mathematicians that do, I probably wouldn't have noticed this looking at the talk, but this one might look familiar. This was actually a path-ordered product that we computed. When we were looking at the cluster scattering diagram example for this same exchange matrix, and we applied a path-ordered product to x, sorry, typo there, x1 to the minus 1, we got x1 to the minus 1 times this polynomial. So that's not a mistake. Let me try and just mention now some theorems. So first of all, it's a theorem of Fomin and Zelevinsky, which I just referred to on the earlier page, that each cluster variable is a Laurent monomial in the x's times a polynomial in the y hats. And that vector that's giving the exponents of the Laurent monomial is called the g vector of the cluster variable. Another theorem, which is Gross-Haken-Keelan-Kontsevich, part of the cluster scattering diagram cuts out the cluster fan. So the cluster fan is, remember my cluster variables come in these clusters of n. Well, it turns out if I take the g vectors in the sense of this previous theorem, the g vectors of each cluster variable in the cluster, those are linearly independent, and they span a cone. And if I take all those cones together, we could call that the cluster fan, and that's living inside the cluster diagram. This is the cluster scattering diagram, sort of as a sub-fan of the cluster scattering fan. Another thing to that I want to mention is how cluster variables connect to theta functions and other things. So I'm going to actually phrase it in terms of cluster monomials. A cluster monomial is just a cluster, a monomial in the cluster variables in some cluster. So I have some cluster variables in my cluster. I can take non-negative powers of those, multiply them together, I get a cluster monomial. But there's a cluster monomial for every rational point in the cluster fan. And the theorem from Gross-Haken-Keelan-Kontsevich is that any cluster monomial is just a theta function. Another theorem, I mean, morally this is Gross-Haken-Keelan-Kontsevich because it just sort of falls out of something that they did. But it hadn't been written down anywhere, and I had a lot of fun noticing it. And I'll be honest, the way I noticed it is I sort of walked you through that because I was just doing this example of path-ordered products, and I said, wait a minute, that looks like a cluster variable. It turns out that if you do the right path-ordered product, you can get cluster variables or cluster monomials as well. So what you need to do is you need to take the g vector of the cluster monomial that you want, and that will be, you'll take x to that g vector. That's the monomial you'll put into a path-ordered product. And the path-ordered product needs to start near that g vector and go back into the positive cone. So I'll try to sort of point to this picture with my mouse. We had a path that started here and went back to the positive cone. Well, the g vector that we started with x to the minus 1, x1 to the minus 1 was really a vector pointing in this direction. And so we started near that and went home. Okay, so again, just want to now take that and expand on it. Cluster monomials correspond to theta functions for theta in the for you know, if you take you know, a g vector in the cluster fan, you get a theta function. And maybe I'll use the term return function. Return functions, somehow you're starting at lambda, starting at your g vector, your particular integer vector, and returning. And you're returning in two senses. First of all, you started with a monomial that is just at that vector, x to that vector. And also your path starts near that vector and goes to the positive cone. So we'll call that a return function, that certain path-ordered product applied to a monomial in the x's. And the theorem that was on the previous page says cluster monomials correspond to return functions for lambda in the cluster fan. So, but the point is either one of these things, theta functions or return functions, you can do them and they're just fine, even if you're not in a cluster fan, even if you're not in the cluster fan. If you're starting with a vector that's in the cluster fan, in other words, a vector that somehow morally lives in the cluster algebra, then you're going to get theta, you'll get that cluster monomial out. But if you start with something else, you can still do theta functions and return functions. theta functions, if you're thinking about cluster scattering diagrams, and even if you're thinking about other kinds of scattering diagrams, I think theta functions are on everybody's radar screen. Return functions are not on most radar screens. And now on my slide, I have two questions that if you walked in off the street, you'd know my answers for them. Because are they the same as theta functions? Obviously, I mean no to that. And are they interesting? Obviously, I mean yes to that, or I wouldn't have asked either of those questions. So theta functions are not the same so return functions are not the same as theta functions, and they are interesting. And I'll try to say a little bit about why they're interesting too. Okay. So quickly to an affine rank 2 example. In this case, this cluster fan, basically the G vectors of cluster monomials, they take up all the space except for this one limiting ray that's in this slope -1 direction here. We could ask ourselves, so we know that, you know, theta functions and return functions are just giving us cluster monomials everywhere. But what are return functions giving if we start on this this limiting ray? It's not a cluster variable. It's got to be something else. Well, it turns out that if you do the return function, so you're always going to get a monomial in x1 inverse x2. You're gonna get that monomial you applied the path ordered product to, and that'll be times some power series in the y1, y2s that comes from all these wall crossings. If I start numbering my cluster variables as shown in the picture, two things happen with this return function. First of all, you know, I can basically write this return function as a limit of ratios of cluster variables. The way I'm going to do it is I'm going to recall that each cluster variable is like x to a g vector times some polynomial in the y hats. So this formal power series that you get is actually a limit of ratios of these adjacent polynomials that you know, they're called F polynomials, these pieces of the cluster variables. And if you take that limit, you actually get this thing that looks kind of like a Catalan or Narayana generating function. I should mention that for different reasons, Chanakji and Schiffler calculated this limit of ratios slightly before I did. But it's essentially the generating function for Narayana numbers. So somehow this return function is counting Narayana numbers. If you're not familiar with Narayana numbers, you know, there's Catalan numbers which count sort of everything in numerical, in enumerative combinatorics. Narayana numbers are a refinement of those, sort of a two variable, they take two inputs instead of one input, a two parameter refinement of Catalan numbers. And then just to get into the third piece of this talk about scattering, who knew that this was mathematical physics? I put this paper on the archive, and I started getting, I got cited by some physicists, and I got invited to a mathematical physics seminar to talk about this stuff, which was a real trip for me because I was a physics major as an undergrad, but I don't do anything now that could be considered physics. I guess until this, I still wouldn't say I'm doing physics in any sense. But let me try to tell you in which sense this is mathematical physics. So what are scattering amplitudes? So scattering amplitudes are, in some sense, are as rooted to the ground, non-esoteric, non-theoretical, in some sense, physics that you could want to do. You shoot particles at each other, and you see what the probability density is for where that particle goes. And okay, maybe there's probabilities of it changing into another particle and whatever. But this is somehow something you can measure. As a young physics major, I actually once helped do this kind of measurement. My job was to move the lead bricks to shield the instruments from extra radiation that was going to come out of these scatterings. But it's that kind of physics in some sense. Now, there's a lot of theory that's going on about it, and so we're tying into the theory. People want to be able to predict these probability densities rather than just measure them. And you can do this, in some sense, it's a sum/integral over Feynman diagrams, but in practice, these computations are really complex. when the answers that you seem to get out of these computations, if you do them up to low order, you get tensor products of really they're polylogarithms, but you can encode that as tensor products of certain symbols, so just certain functions of x1 through xn. And the current hot idea that's been told to me is that people would like to just skip the Feynman diagrams and just skip to the answer. Is there some way we can just understand it? Now we just need some functions. We need some functions of x1 through xn. Can we skip the Feynman diagrams and just directly find out why do we get these functions? What are they? So in some sense, what we would need is a machine that makes functions. Now, people have observed that in some cases, the symbols are cluster variables, and the compatibility of, compatibility, because remember, cluster variables can be in a cluster together or not. And in some cases, compatibility, whether those two symbols are in the same cluster of cluster variables, is telling you whether they can appear together in these tensor products. Again, this is just really the lightning fast overview. In more complicated symbols, in more complicated cases, there are also irrational symbols, which the cluster variables are rational functions. They can't be irrational. But it turns out that these irrational symbols are looking like theta functions and also return functions, and that's I think how my paper came to be mentioned in a mathematical physics paper. So the question is, can we compute these irrational symbols? Can we use now this bigger fan that includes space outside where the cluster variables live to describe some sort of adjacency, which symbols can appear together? And the upshot is that we want combinatorial models. So maybe that's a good place to move on to combinatorial models. But are there questions? I think I'm going to just not say the recap, but if there are questions at this point, it'll be fine.
No, I don't think there's any questions.
Okay. So let me go on to combinatorial models. So just to recall, what we have a skew symmetrizable matrix B, some specific one. It would be good to know the cluster variables, the scattering diagram, the scattering fan, the theta functions, and the return functions. And so my research, even before I understood the good connection to physics or the possible connection to physics, was this is what I wanted to do anyway. It's wonderful as a mathematician, as I'm sure you know, if there's something you've been really interested in and then somebody else, then there's some reason that you can do it that somebody else is interested in too. That's always a fun thing. So let me tell you about some of the combinatorial models. So first of all, there's finite type. In finite type, there's only finitely many cluster variables. And a cluster variable is a finite type if and only if, well, basically, there's blank space because I have to fill in the real truth. But the partial truth is, if I take this integer skew symmetric matrix, I can just ignore the signs, turn all the entries negative, and put positive 2's along the diagonal and have a Cartan matrix. So if that Cartan matrix is a finite type, then I get a cluster algebra of finite type. Okay, so then somehow this infinite, this infinite tree of possibilities of getting cluster variables, it sort of loops in on itself and gives only finitely many different answers. The real answer is that B might be mutation equivalent to an exchange matrix whose Cartan matrix is a finite type. So maybe you have to mutate B 3 steps and then its Cartan matrix is a finite type. So that's the answer there. And there's sort of a one-step way to check this also that people have looked at. Cluster variables are always Laurent polynomials, and their denominator vectors are almost positive roots in a root system for A. So I've got this finite root system of finite type. Sorry, I've got a Cartan matrix of finite type. There's a root system associated to it. And it turns out that if I want to know which denominators happen in my cluster variables, I'm getting either positive roots. I'm getting the simple root coordinates of positive roots, or I'm getting the negatives of the simple roots. And that's why I say almost positive roots. The negatives of the simples are almost positive. Okay, so and there's a bijection. Cluster variables going to almost positive roots. That's a bijection. That's their theorem. There's also a combinatorial description of when things are adjacent. So as an example, we looked at this very example. Turns out that the Cartan matrix associated to it is for a root system of finite type A2, and these are the almost positive roots, and these are the denominators. here we see honest denominators. Here, this is a denominator, which really looks like the denominator is x1 to the -1, and that's why we get a minus alpha 1. Okay. I think I'm going to actually have to skip compatibility, but there's a way to do compatibility. When do two almost positive roots represent clusters that are in the same, cluster variables that are in the same cluster? Well, you can do something just in terms of the combinatorics of roots. And in this case, there's going to be some stuff that goes by. In the case where your Cartan matrices of type A, you're actually just doing triangulations and flips. You're getting the isosahedron. So this triangulation, for example, represents three cluster variables represented by the three diagonals of the hexagon that I drew in. And if I wanted to remove one of those, I'm moving to a different triangulation. Okay. Another approach to finite type is that we remember some of the extra information from the exchange matrix. There's some sign information, and so we can think about for a skew symmetric matrix, I could have put the minus here or there, and whether I do or not is going to basically tell me whether S1 is before S2. I'm thinking of the simple reflections in my Coxeter group. I've got a root system, I've got a Coxeter group, and this sign information is telling me in what order I should multiply the simple reflections. So we think of this B as giving us a root system, and therefore a Coxeter group, and also a Coxeter element in that root system. So the cluster fan in this case is just what you could call the Cambrian fan. I will say C Cambrian fan because it depends on this data, the sign information in B. And the way you construct that is you can do it with the combinatorics of reduced words. So there's this whole picture where you work with the weak order on a Coxeter group and playing with reduced words for elements in the Coxeter group and special reduced words. And you can end up building this Cambrian fan. And the way you do it, you start with all the reflecting hyperplanes for this root system, for this Coxeter group, and you're taking pieces of them, and the Coxeter element tells you how to do that. If you're not familiar with this kind of picture, this is meant to be a stereographic projection of a three-dimensional fan. So if I've got a fan in three-dimensional space, each of it, and it's a simplicial fan, so each of its cones is just the non-negative linear span of three rays. Well, I can look at where all those cones intersect the unit sphere, so I'll get these sort of spherical triangles on the surface of the unit sphere. Then I'm taking a stereographic projection to turn them to circles on the plane, and that's what we're seeing here. Opinions can vary even among co-authors as to whether these pictures are comprehensible or not. I love them. David Speyer, who I did some of this work with, doesn't like them so much. Anyway, as a quick example, if we're looking at the Coxeter group of type A3, which happens to be a symmetric group, this is the fan cut out by all of its reflecting hyperplanes. If I zoom in a little bit, what happens is certain elements are declared to be sortable, and then we use them. They each sort of grab some other cones in the fan that glom into them, and so we coarsen our fan by sort of gluing together the pieces that used to be separate cones, and then that's our fan. So this is some of the ways things play out in finite type. Let me spend maybe 3 or 4 minutes just trying to show you how things play out in affine type. Affine type's been something that David Speyer and I, and also Salvatore Stella and I, have been thinking a lot about recently. Salvatore and I are still in progress with some things that I'll tell you about. But there's 2 different ways to think about affine type. And again, in a more general setting, people have a different definition. For me, this definition works. One is that our exchange matrix, although our exchange matrix determines a Cartan matrix, and that Cartan matrix is no longer of finite type, but it's of affine type. And again, maybe mutation equivalent to something like that. Another equivalent way to say it is that our cluster algebra has infinitely many cluster variables, but it does have linear growth. Okay, for 2 by 2 matrices, that distinction breaks down. But And we can model this completely. There's two ways to model the affine type case. One is an affine almost positive roots model, and the other is a doubled Cambrian fan construction. So in particular, these models, you can build the cluster scattering diagram and fan explicitly using something called shards. Just throwing that word out, it won't come up. But pieces of hyperplanes, basically. And Salvatore and I are in progress to construct all the theta functions, so that if you knew all the, you can get all the cluster variables using mutation, so you can get all the cluster monomials, and then the remaining theta functions, and also how they multiply, how they exchange in some sense, and also work in progress to construct this return function. Let me try and tell you a little bit about that. So first of all, the way you get an affine root system is you start with a finite root system. In this case, we'll start with A2. So we'll be looking at A2 tilde, which is the associated affine root system. And what you do is you construct the affine root system by what I'm doing between these two pictures is I'm sort of turning this so that it's not in a plane parallel to the screen, but remember thinking of it as being in a plane that's sort of a little more like sort of curved, bent into the screen. And then we need copies of it. So we take copies of this root system that are just related by translation. And we also can include imaginary roots. So imaginary roots are copies of the origin. We don't want the origin itself. We don't want the zero vector, which was here, but we can take translations of the zero vector, and those are imaginary roots. And then some of them are positive and some of them are negative, in a similar way to how one had positive roots and negative roots in the finite case. And we want to restrict to ones that are almost positive. So really, the ones that are either positive or just barely negative. So those are the ones that are just barely negative. So we'll get rid of the rest. And these are our almost positive roots. We can restrict further to the almost positive sure roots, which is, well, there's a way of saying this that I probably need to breeze over, but we take out of there's a certain hyperplane that intersects our root system, and we keep finitely many things out of that hyperplane. So we've got this root system, this set of almost positive sure roots, and it turns out these are the denominator vectors of our cluster variables. There's also a limiting thing. So this thing here is an imaginary root in the middle, and the directions of all the other roots as I go in these infinite sequences of roots, they limit in direction to that. Okay, so let me just try to tell you, and I probably will have to stop after this. Let me try to tell you what facts we know here. So first of all, almost positive sure roots, they show up in two ways in cluster scattering diagrams. First of all, they index the rays of the fan. For this infinite fan, all the cones in it that are rays are indexed by these almost positive roots. This imaginary almost positive sure root is indexing sort of a limiting ray, like we saw, and we'll see a picture that I'll end with. Also, the positive sure roots, if we ignore the negative sure roots, just only take the positive sure roots, those are the normal vectors to walls. So somehow this set of roots is telling us everything about the cluster scattering diagram. And the thing that I won't have time to say much about is that you can actually, starting with these almost positive sure roots, you can give descriptions of the walls by, you give linear inequalities that tell us, okay, it's the part of this hyperplane satisfying these linear inequalities. Let me just go out on the picture. So this is the sort of a rank 3 affine case. So this is a 3-dimensional fan. We have the limiting ray indexed by the imaginary sure root. We have these two special sure roots that are not imaginary roots, but they are compatible, or then somehow they're in the same cone with the limiting ray, and then we have the rest. I think I probably ought to stop here and just ask if there are any questions. I didn't quite get to my goal of 50 minutes plus questions, but any questions here?